Okay. So in the previous lecture, we in the lecture 7, lecture 6, we have discussed about the isomerism, and also we have discussed about the alkene, how alkenes looks like, and some of the alkene we have taken from the textbook, and we have discussed their nomenclature, IUPAC name, how their nomenclature looks like. So in this lecture, we'll discuss about the the alkenes. So as the cis, also we have discussed about the butene molecule. Butene can show the geometrical isomer in two ways. One is the cis isomer and the other one is the trans isomer. So in case of cis isomer, cis isomer and the trans isomer boiling points are different. You can see the cis isomer, cis butene, where the two methyl groups are opposite, same in the same side. You can see the two methyl group and the same side the double bond. So that's why it is act as a cis butene, and the hydrogen molecule also are in the same side. So that's why it is a cis molecule. And in case of trans molecule, where the methyl group is anti to another another CH3 group, that means almost 180-degree far apart to the single bond. So that's why it is known as the trans but 2 in. 2 in why? Because if you start from any carbon 1, 2, 3, then it is a 4. So that means the in the 2 position one double bond is there. And why but? Because 4 carbon is present. So that's why but and 2 in. And in the same way here also, only in the case of cis we'll just add the trans but 2 in. But in the both cases, if you see the physical properties like boiling point, melting point that will be different. In case of cis 2 butene, boiling point is much more higher compared to trans butene. So cis form of is the also, and the other way around, cis form as of the alkene is found to be more polar compared to the trans form. For example, dipole moment of the cis 2 butene, as they are saying, so dipole moment of the cis 2 butene is the 0.33 divide. Okay, whereas the dipole moment of the trans form is almost zero, or it can be said that trans butene is the non-polar. Why? I'll show you the example in the next slide. So let's say CH3 molecule, the dipole moment in that way, in this way, and this CH3 molecule also the dipole moment is the in this way. So that means one dipole moment is this way and another dipole moment is in this way. So that's why the dipole moment more. Actually the polarity depends on the dipole moment. The moment if you have a dipole moment is the almost zero, is already cancel out each other by the opposite direction. So that's why the trans to butene is almost non-polar, you can say. And this can be understood by the drawing the geometrical isomer of this one. So if you draw this one in the geometrical isomerism, if you want to see, I have taken the example photo from your textbook. So where you can see the delta plus is CH3, where this CH3, this one is the delta minus, let's say, suppose. So, and suppose C is 3. So the dipole moment electron density is coming here. So this carbon is delta minus, this carbon is delta minus. So what happened? The dipole moment electron density is coming from CH3 to in this way. Okay, where the electron density is coming. So dipole moment in this case, CH3 case, dipole moment is in this way. And here in this case also dipole moment is in this way. So that's why the CH3, although there is not cancelling out, so but here it is actually the electron density is coming to the central carbon. So that's why there no such cancelling out of the dipole moment. But in case of trans, you can see one is going here, another is going here. So the actual moment is the in this way, and here also the actual moment in this way. So that's why. So let's say this one and this one. So that's why almost cancelling out. So that's why the mu equals to or mu or the dipole moment equals to 0 in the case of trans, and the cis butene that is a 0.33 divide. Okay, 0.33 divide. Now the case is the preparation. Then how we can prepare this kind of molecule? Okay, so now the question is alkynes on partial reduction with calculated amount of dihydrogen in the presence of pelletized charcoal partiality deactivated with poisons like sulfur compounds or quinoline gives the alkene. Why there are we have to use the poisonous like sulfur compound or quinoline compounds? Because if you don't give any means poisonous like sulfur compound or quinoline compound, they can be if you start from this let's say any alkyne moiety. I'll come to the example. So if you start from this kind of alkyne, it will never stop in this stage. Suppose R and this R. So you want to, if you use want to palladium, charcoal, and hydrogen, and you if you are using any poisonous like sulfur compound or quinoline, sulfur or quinoline, so you can actually end up in getting means you can stop the reaction in the alkene step. You can stop the reaction in alkene step. So if you don't use this sulfur or poisonous like quinoline or sulfur, it can further go for the hydrogenation of this one, and then you will end up in getting the C C single one. C C single one you will end up. You will end up in getting single one. Okay, but in this case, what will happen? So here, as we are using the palladium charcoal and as a poisonous quinoline or sulfur, so that's why we can stop the reaction in the alkene step. So we are now going through the how we can synthesize the alkene moiety. Although we have discussed about the alkene moiety, how we can prepare that part we have discussed in the past few lectures. But in this today's lecture or previous lectures, we are discussing about how to synthesize the alkene molecules. Now, actually, the catalyst we are using palladium, charcoal, and hydrogen. So this is the combination. The combination actually called one catalyst, and this is the catalyst name is the Lindlar catalyst because Lindlar, one scientist, he has isolated he has discovered this reaction and that's why the reaction or the catalyst itself named as a Lindlar catalyst. Lindlar catalyst. Okay, now we'll go to the not only Lindlar catalyst, liquid ammonia also can reduce the alkyne part. Then how it will reduce? So as you can see, so this is a Lindlar catalyst. So I have taken some example from the textbook. So Lindlar, this is a Lindlar catalyst. Okay, suppose this is a Lindlar catalyst. Now this Lindlar catalyst actually it is giving suppose R1 and R2 in the same position. So now it is a cis alkene, right? This is a cis alkene. Now suppose so Lindlar catalyst is giving the cis olefin, cis alkene. Now if you use the sodium and liquid ammonia, what it will end up in getting? So the hydrogen will be opposite to each other. This hydrogen will be opposite isomer, opposite to each other. Now, so let's say if you have the alkyne and the hydrogen molecule, now they are now you will end up in getting instead of cis alkene. So in the previous case, if you use the Lindlar catalyst, you will get the cis alkene. When you will use the sodium and liquid ammonia, you will get the trans alkene. This is called trans alkene. This is called trans alkene. Now you have a now the two example we need to know whether how we can synthesize the cis alkene, how we can synthesize the trans alkene. If you anywhere if somebody asks that how we can synthesize the trans alkene, then you have to use this sodium and liquid ammonia for this purpose. And if you suppose you have a acetylene moiety, this is simple CH that is called CH triple bond CH. You have a simple acetylene moiety. Acetylene moiety in the presence of Lindlar catalyst. That is hydrogen molecule and the Lindlar catalyst. That is palladium charcoal and Lindlar catalyst. Then what you will get? Lindlar catalyst. Lindlar catalyst. Then what you will get? CH2, H2 double bond H2. That is for alkene moiety. That is also alkene, but this alkene has a specific name. So this alkene also known as the ethylene molecule. This is called ethylene molecule. and this is the acetylene moiety. This is the acetylene moiety. Now you have a suppose propine. Propine means what? This is the acetylene and this is the propine. This is the propine. One propine. This is called one propine. Okay. So why one propine? Because if you start from one carbon, two carbon, and this is a three carbon. So in the one carbon there is a one alkyne moiety is the present. That's why it is called as the one propine. Now one propine in the presence of Lindlar catalyst, in Lindlar catalyst, one propine in the presence of Lindlar catalyst, what will happen? Lindlar catalyst, Lindlar catalyst, what you will get? CH3, CH, and double bond CH2. This is hydrogen, and this is also hydrogen. So this is called one propene. One propene. Okay, this is called one propene. If you start from the one propine, and this is called one propene. Okay, now we will end up in getting the one propene, and in the presence of what? A Lindlar catalyst. And now from alkyl halide. So what is alkyl halide? We know that alkyl halide in the periodic table what will happen? In the periodic table you can see. So you have a fluorine atom. You have a the first is the halogen moiety is the fluorine, then chlorine, then bromine, then then it is iodine. Okay. So anywhere if you see this CX and X equals to what? Halogen molecule. Halogen molecule. Halogen may be Cl, iodine, Cl, chlorine, bromine, iodine. So okay, so they are saying that from alkyl halide also we can get the alkene moiety. How? So alkyl halide on heating with alcoholic potassium, potassium hydroxide dissolved in alcohol, say ethanol, eliminate one of the molecule of halogen acid to form the alkene. So halogen acid means what? HX. Whether it is HCl, whether it is HCl, that means also hydrochloric acid. That is hydrochloric acid. Hydro hydrochloric acid. That is called hydrochloric acid. And if you have the HBr, if you are generating HBr, then what will happen? If you are generating HBr, then you will get the hydrobromic acid. Hydrobromic acid. Hydrobromic hydrobromic acid. Hydrobromic acid. Suppose you have a HF, okay, HF, that is hydrofluoric acid. Hydrofluoric acid. Hydrofluoric acid. Hydrofluoric acid. Okay. Now you have this X equals to chlorine, bromine, and iodine. Okay. Now you have a base. And then now the how the mechanism it looks like. So let me first erase all this compound. Then suppose you have a C C. Now you have a hydrogen here and another X is here, another hydrogen is here. Now you have another hydrogen present is here, hydrogen is here, and now you have another hydrogen molecule here. Okay, so let's say you have this alpha and this is called beta. Okay, now X equals to you have a X equals to they are only saying chlorine, bromine or iodine. Chlorine, bromine, or iodine. Now you have a alcoholic base. KOH alcoholic base means KOH alcoholic base. Okay, base means so in the presence of alcoholic base, it will act as a OH minus. Now it is a alcoholic minus is a base. Now this base will abstract a proton from it will come here and it will abstract a proton from here. Now let's say this is it will abstract proton here. Now it will come this position. Now then it will comes out. So that means you are generating CHH double bond CH. So you are in one pot, you are generating alkyl moiety. You are actually generating alkyl moiety from where? Alkyl halide. So this is a alkyl halide. So this is the main mechanism, alkyl halide. Now the question is not only the simultaneous reaction it is happens, right? The nature of determinants the rate of the reaction. It is observed that the rate is iodine and the group, the tertiary, primary, and the tertiary secondary and the alkyl group. While for the alkyl group it is tertiary, secondary. The nature of halogen and the alkyl group determines the rate of the reaction. Now they are saying, suppose you have a suppose suppose you have a iodine, chlorine, or bromine. So when you are going from chlorine to iodine, so there is a chlorine to iodine means the Ci bond length is much more higher compared to Ca bond. Okay, Ca bond. So this bond length is in case of Ci is much higher compared to Ca. Now this Ci is a loosely bound bond with carbon. Now in the presence of base, what will happen? So first, if it is this bond is loosely bound, then it will generate one carbocation, and we know that it depends on the carbocation stability. So suppose it is going via a carbocation molecule. Now, suppose CH, and if you have a X in the presence of X, so let's say I am taking an example of the iodine. Now let's say C hydrogen, hydrogen, and this is a let's say iodine. Now, as we know that the Ci bond is not much tightly bound, so that's why you will generate CH, CH, and this CH2, and then there will be one positively charged on the carbon atom. Okay, this is a positively charged carbon atom. Now, this in the presence of base, what will happen? So base will come and deprotonate your hydrogen molecule. Now this deprotonate will happen, then you will end up getting the minus minus of BH. Okay. Now suppose OH minus is your base. Now the moment it will take the OH minus and H plus, it will generate one water molecule. Water plus your alkene moiety. Okay. So now it depends on the fluorine atom, halogen molecule, whether it is a fluorine, chlorine, or iodine, or bromine, or also it is depend on the carbocation stability. And you know that the tertiary carbocation is much more stable compared to the secondary and the primary. So when you have a tertiary carbocation, when you have a chance, the reaction will go faster compared to the secondary and the primary. Okay. Now we'll go to the from vicinal dihalide. Now, from vicinal dihalide, so in the previous slide, we have discussed about only about the we have discussed only the single halide molecule, alkyl halide molecule. Now, suppose you have a dihalide molecule. Dihalide means what? Dihalide means two X molecule will be present. Now, this kind of molecule, when you have a this CH2Br, CH2Br, sorry. So suppose you have a CH2 and then another CH2. So this is a one beer here and another beer here. Now you have a zinc molecule. So in the presence of zinc, what it will form? It will form first the zinc bromide, CH2. So zinc will go and insert in the carbon and halogen molecule. So first it will form the CH, CH2, Zetten beer, Zetten, Zetten beer, and this is also another beer. Now it will go here and beer will come out. Then what you will get? You will get the zinc bromide, zinc bromide Br2 plus this alkene moiety CH2 double bond CH2. So from dihalide also we can end up in getting the alkene moiety. Now suppose you have a three carbon chain. So another example I have taken. So there where the three carbon present. So CH3, then CHBr, and then CH2Br, and then CH2Br plus G. Now what it will form the same way. First it will go and bind there CH3, CH, then CH2, and then ZnBr. ZnBr, and it is a Br molecule is here. Now where it will go here, a zinc bromide will come out. Okay. Now what we are generating? ZnBr2, ZnBr2 plus CH3, CH, CH double bond, CH. Okay. Now we are generating this one. Okay, now the main thing is the now the from alcohols by acidic dehydrogenation. From alcohols by acidic dehydrogenation. So suppose now we have discussed about the alkyl halide. Now you have a suppose alkyl alcohol. Now so we know that the alkyl halides are good living group, but you when you have the alcohol moiety, how will how will you go for the halogenation? Means not halogenation, dehydrogenation, uh, de uh, dehydration means OH is not a good living group. So first we have to make it for the good living aptitude. So for that either we have to go for the protection of the OH molecule, or else we have to go for the protonation and acidic condition. So in acidic condition, what will happen? So you have a suppose alcohol OH. So in alcoholic position, OH is the oxygen has a good proton acceptor. So it can go and easily take the proton from the OH molecule. Then what will generate? OH2 plus. So now it is a good living group. So the moment you get the protonated through the OH position, then the OH2 water molecule comes out. Then you will generate one carbocation. So the moment you have the carbocation, then there will be one proton abstraction by the nearby to that carbon, so that it can fulfill the octet tetra sorry not octet tetravalency of the carbon molecule carbon atom. So for that purpose, we'll see the mechanism it's go how it will go. So that's why I have taken one example. So let me draw the compound first. So CH, you have a CH molecule, CH, and then CH molecule, and now you have a C hydrogen is here, and then another hydrogen is present here, and then OH group is present here. Okay. Now in the presence of H2SO4 and heat. H2SO4 and heat means it will present first in this way CH, and then OH2 plus. So then this OH2 plus will comes out as a water molecule minus H2O. Then what will generate? CH3. Then this is a CH2 plus. Then in the presence of base, it will extract the proton from here. Now it will go and comes out here. Now what will generate? CH2 double bond CH2. Now in this way, we can also, this is called the ethylene molecule. This is called ethylene molecule. So we are starting from the ethanol, ethylene. We are starting from the ethanol molecule, ethanol to ethylene, ethanol to ethylene. Now the question is the chemical properties. So you can see the as we know that the alkenes are the rich source of the loosely held pi electrons. So due to which they show addition reaction in which the electrophile can add onto that carbon-carbon double bond. So you know that this alkene double bond is loosely bound double bond, loosely bound this double bond. Now you have a electrophile that is known as the E plus electrophile. Electrophile, that is we are denoting as a electrophile. Electrophile means there is no such, so they have a tendency towards the go towards the electron rich compound. So electrophile. Electrophile means electron deficient species. That is a electron deficient species. Electron deficient species. Electron deficient species. Electron deficient species. Okay. So now you have a electrophile. So in the presence of electrophile, what will happen? So electrophile will come and will go there, E plus, and then what it will generate? So C plus and then C E, hydrogen gets. So then carbon is, because the electron density is loosely bound and also electronically very rich of the alkene moiety. So that's why the electrophile can go and then add on the add on the alkene system. Now addition of the dihydrogen molecule. So addition of the dihydrogen molecule is alkane on the platinum 6. So let's say you have a CH2 molecule. This is a simple example how the hydrogen molecule go and bind the CH2 and in the presence of platinum, charcoal and hydrogen. How the mechanism looks like. So let's say now you have a hydrogen molecule. Hydrogen molecule is the one HH bond is present here. Now, so this actually you have a metal surface. So that's why they have used the platinum charcoal. So metal surface means they are go and bind there. Now this, you know that this is the alkene moiety. Okay. And the hydrogen molecule will start to form a bond in this way. Okay. Now they start to lose their this bond. They start to break this bond. Then there will be a bond formation between CH2 and hydrogen. Then there will be one, this breaking started already. Okay, this hydrogen bond breaking already started and this bond making already started. Now it will go and fully break this bond and then by what you will generate CH3 and then CH3, CH3 and CH3. This is how the dihydrogen molecule go and bind the go and add to the alkene moiety. Now we'll discuss about the uh, now we'll discuss about the how the halogen molecule can go and add to the alkene moiety. Now, in the presence of, but we need one, actually we need one solvent to for the reaction because anyway, without solvent, the reaction is not possible, right? So we need one solvent so that it can, both the reactant and the catalyst can go and dissolve there. In this, until unless this is not dissolving, the homogeneous solution is not forming, then there is a, then the reaction cannot go proceed to the further step. So that's why we need one solvent also. So for that purpose, what we will see. So in the case of bromine molecule, so if you want to add the bromine molecule to a alkene moiety, so how it's go? So first they choose the CCl4 as a solvent, CCl4 as a carbon, CCl4 as a carbon tetrachloride, CCl4 is a solvent. So you can see CCl4 is the solvent molecule they have used. So how the bromine molecule go and add to the alkene moiety? Let's see. So CH2 double bond and then CH2. So now CH2 double bond CH2 plus Br2. Now this Br2 under CCl4 condition, under CCl4 condition, what will happen? It will form the CH2Br and CH2Br. How? So first it will form the Br2. Here we don't need any catalyst. Without catalyst also this reaction is going. Okay. So now it will form, first it will break this bond. Then it will start to make this bond here. Now what it will generate? CH2, CH2Br, CH2Br, and this bond will break, and this bond will generate here CH2. Okay. Now you will end up in getting the this CH2Br, CH2Br, and CH2Br. Okay. So in this way, the bromine molecule can go and add. Now you have a Cl2 molecule. We have seen the how the bromine molecule can go and add on to the alkene moiety. Now if we change the alkene moiety, instead of ethylene, if we take the propene molecule and if we see the Cl2 molecule, how it looks like, how it will go. Although the bromine molecule addition is not so easy the way I show you, but I will show another example and another mechanism how it will go, the bromination of the alkene. But first we will discuss about the chlorination of the alkene moiety. So the chlorination of the alkene moiety is how it is look like CH3. So let's say we have taken propene molecule, CH3, CH, and then double bond CH2. Okay. Now you have a Cl2 molecule, Cl, and there is also Cl2. Now, in the presence of CCl4 or any other solvent, okay, CCl4 let's say, so then what you will generate? So one Cl will come here, another Cl will come here. Okay, so let's say this is a Cl, this bond making started, then this bond breaking will started, and this bond formation will happens. Then what will generate? Will generate CH3. Will generate. Will generate. What will generate? Will generate CH3. Then CH3, CHCl, CH, and then CH2. Here also one Cl, and then here also one Cl. So this is a 1,2 dichloro di dichloro dichloropropane dichloropropane. Okay. Now then we'll go to the hydrogen names. Hydrogen. So hydrogen halide. Addition of hydrogen halide add after the alkene to form the alkyl halide. We have seen the how the from the alkyl halide how we are generating alkene molecule. Now the reverse way we can think about the how the alkene halide the order of reactivity is the HI is the faster compared to the HCl. Okay, like the addition of halogen to alkene molecule, addition of hydrogen halide is also example of the also example of electrophilic addition reaction. Let us illustrate first this one. Okay. So let's say you have a one alkene moiety. Suppose CH2, CH2 double bond, CH2. You have taken a simple example that is ethylene molecule, the first alkene moiety in the hydrocarbon family, CH2 double bond, CH2. Now you have a HBr. So from the HBr, we what we know? We know that the Br is delta minus and H is delta plus. Why? Because bromine is much more electronegative compared to the hydrogen. Now what we will get? So because we have taken the symmetrical alkene, symmetrical means what? If you put a mirror image here, it is just a same. But unsymmetrical alkene is what? Symmetrical alkene. So now you have a symmetrical alkene. Now this hydrogen go and add. So suppose hydrogen will add here or bromine will go and add here. So still you have a chance the same molecule you can generate here. Okay, same molecule you will generate here. Now you have a CH3. If the hydrogen and bromine, so let's say hydrogen will go and add here and bromine will go here. So then what will generate? CH3, CH2 and then Br. Okay, now you will generate this one. Okay, now addition of whatever the alkene in the textbook they have shown all are symmetrical alkene. So symmetrical alkene, and again we will discuss about the another symmetrical alkene, that is a 4 carbon containing chain. So suppose CH3, you have a CH3 molecule, CH3 molecule, then you have a CH, CH3 CH double bond, and then CH, and then CH3, and then CH3 molecule. Okay. Now you are adding a HBr molecule there. HBr molecule here. Now what you are generating? So H is here and Br is here. Now CH3, CH, CH, and then CH3. So here it is bromine, and here it is hydrogen. Okay. So now you are generating a H and Br molecule. So far we have discussed about the symmetrical alkene. Let's talk about the unsymmetrical alkene. So when you have an unsymmetrical alkene, so how it is looks like, how the reaction will go. So let's say now unsymmetrical alkenes, how the reaction will go. So let's say unsymmetrical alkene is a 3 carbon chain. So let's say CH3, CH, then double bond. Okay. Now you have a Br2 molecule, a HBr. So there is a two possibility. So either hydrogen come here and bromine come here, or else hydrogen come here and bromine come here. So let's see. First we will draw the two structures. So CH3, CH, Br, and then CH3. And then CH3, CH2, and then CH2. It is a Br. Now there are two possibilities you can see. One is and two. In the one structure, what happened? Two bromopropane. And the second structure, one bromopropane. Okay, one bromopropane and two bromopropane. So structure one and structure two. But if you see the Markovnikov rule, so the addition, there is a one rule that is called the Markovnikov rule. That is called the Markovnikov. We have to know this rule. Markovnikov Markovnikov rule. So what is Markovnikov rule? Markovnikov rule is in the presence of HBr. So the negative addendum will go to that carbon which leads to the higher means the which leads to the more stable carbocation. So what happens? So the negative addendum, so the negative addendum, negative addendum will go to that carbon, will go to that carbon. Negative addendum will go to that carbon where where it will give the where it will give where it will give the more stable carbocation, where it will give the more stable carbocation, more stable carbocation. Okay, now we'll see the mechanism, how the mechanism it is looks like. And the mechanism is, so CH3, then CH, then it is a double bond CH2, then it is HBr. Then in the presence of HBr, what it will form? So let's say negative addendum will go to that carbon which leads to the more stable carbocation. Okay. So CH3, CH, then CH2. So one carbocation generation is this one, that is a secondary carbocation, and another carbocation possibility is here, that is called the CH3, CH2, then CH2 plus 2 plus. Now you have a one is the secondary, one is the secondary, but and this is the primary, and this is the primary. So this is secondary and this is the primary. So we know that the We always need the more stable carbocation. So obviously, then from here, if the addition of bromine happens, then what it will generate? CH3, CHBr, and then CH3. So you will get this product only, not this product. And it happens when, so if there is a hydrogen peroxide present, so if you have the hydrogen peroxide happen, then it will maintain the Markovnikov rule or anti-Markovnikov rule. So this is the Markovnikov product, Markovnikov product, Markovnikov product, and anti-Markovnikov product. Anti-Markovnikov. One is Markovnikov product, another one is the anti-Markovnikov product. Okay. Now, now what we'll see? The next one is the Markovnikov actually rule was developed by a Russian chemist made a generalization in the 1869. After studying each reaction in details, the generalization led to Markovnikov to a frame rule called the Markovnikov rules. Okay, Markovnikov, the part of the negative addendum, that is adding molecule attached to that carbon, which was a lesser number of hydrogen atoms, lesser number of hydrogen atoms. Okay, so thus according to the rule, so 2-bromopropane is the expected. In actual, 2-bromo is in 2-bromopropane is the expected product. That means this one, 2-bromopropane is the expected product. This one is the Markovnikov product. But in actual practice, this is the principal product of the formation. The generalization of Markovnikov rule can be better understood in the presence of the mechanism. So in the presence of H plus, okay, so H plus will go and to give the CH2 plus, as it is also showing the same way. So less stable primary carbocation, and the secondary carbocation is the most stable. Sorry. So then what it will form? The more stable, we know that the secondary carbocation is the more stable. So then the Br minus will come, the negative addendum, that is the Br minus, will go and attack to the secondary carbocation molecule. So then we'll get the 2-bromopropane molecule. Now the secondary carbocation, the first one is the secondary carbocation, B is more stable than the primary carbocation, and the former is the therefore the former predominates because it is forming a faster rate. Okay, and the carbocation B is, as I am saying whatever it is saying. So in this way, we'll then the anti-Markovnikov rule, only anti-Markovnikov addition or peroxide effect, or this is called the Kharas effect. So we know that in general it will go in this way. Markovnikov product will always get the negative negative the you'll get the more stable carbocation. But how, if you want to get the 1-bromopropane, then you have to use the anti-Markovnikov rule, that is called the peroxide effect. So in the presence of peroxide effect, it will go via a radical way, where where the Br minus will go and first add to that carbon, where the Br dot, actually Br not minus, will go via a radical way, where H dot Br dot, and H dot Br dot will go fast there, and then it will generate one secondary, means the more stable radical. Then only it will form. So this is the anti-Markovnikov rule. I'll explain the details mechanism in the next slide. But here in the main Markovnikov product is what? Markovnikov product is 2-bromopropane, 2-bromopropane. This is called the Markovnikov Markovnikov product. Markovnikov product. And what is the anti-Markovnikov product? That is the 1-bromopropane. 1-bromopropane is the anti-Markovnikov product. Okay. So in this way, we'll stop this lecture today. And in the next class, we'll discuss about the next slide. Next slide is other than in the next lecture, we'll discuss about the other things. So this is the lecture 7. Another within 5 lecture, we have to complete this lecture. I will bring more things in the next lecture so that we can finish it quickly. Thank you, sir.